In our previous lecture, we completed the revision of electromagnetic induction, and at the end of the electromagnetic induction, we saw the working principle of generator. Okay, and the generator generates alternating EMF or alternating current, and the following chapter, that is this one, tells us or teaches us how to deal with electrical circuits where the current is an alternating current and not a direct current, okay, or a DC. Now, before I revise what generator is and other parts, I want to make one distinction clear between alternating current, we abbreviate it as AC, and the second one is DC. Okay. Now, alternating current continuously changes in magnitude. The most common representation is I equal to Im sin omega t, where Im denotes the amplitude of the current or the maximum value of the current, and because sin omega t can range between -1 and +1, the instantaneous value of our current is going to range from -Im to +Im. Okay. Now the negative sign here is important. The negative sign here is important, which basically tells us that the current is reversing the direction. So current reversal in addition to changes in magnitude are the characteristics of an alternating current or an AC voltage. Changes in magnitude and current reversal. In direct current, for a DC, you might think that DC always has a constant magnitude, but that is not true. DC may vary in magnitude. But the feature that distinguishes AC from DC is current never reverses. Current never reverses its direction. Or alternately, polarities never change. So where have we encountered a direct current which fluctuates? If you remember, when we send alternating current through a rectifier, a full wave rectifier, then you can see, or if you remember, the positive part is maintained, but the negative part is flipped. So because the direction of the current doesn't change, it is not alternating current, but it also does not have constant magnitude. It varies sinusoidally, and here I can write IDC as Im into mod of sin omega t. So please understand that even a DC can change its magnitude, but it cannot change its direction. And for alternating current in this chapter and in this course rather, it will always be I equal to Im sin omega t or sin omega t plus phi, where phi denotes the phase difference between the current and the voltage. Have you understood till this? Yes, okay. Now just a quick revision of generator to carry this point forward. Why is the voltage or the current sinusoidal? Okay, why is the current sinusoidal? The reason behind that is, well, it is associated with the rotational motion of the armature. Okay, because of the rotational motion, the angle theta between two vector quantities, the first one is the magnetic field B bar, and the second one is the area vector, where area vector is the one which is enclosed by the armature, and its direction is normal. So because the angle between B bar and A bar changes, the dot product basically changes, and therefore the flux changes. By definition, flux is the dot product of B bar and A bar, and by Lenz's law, the induced EMF in the coil is negative of d phi b by dt, and that is why the derivative of cos is sine, and hence you get the sine theta thing there. Theta is omega t, where omega is the angular speed of rotation measured in radians per second. In India it is 50 hertz. So this is the main reason why the current that we take, alternating current, has this term in it, sin omega t. You can also write it as cos omega t, but your textbook prefers to use sine, and therefore we are also going to use the sine function. The symbol for alternating current or AC voltage is this one. This is actually a sine curve. This is actually a sine curve. When you enclose it in a circle, that is the symbol for AC voltage source. AC voltage source. It is actually a sine curve. So we denote V as Vm sin omega t. V is the instantaneous voltage. V is the instantaneous voltage, and Vm is the amplitude. Vm is the amplitude or the maximum value. Omega is the angular frequency, and t is the time. In your textbook, instead of plotting t on the horizontal axis, they prefer to plot omega t, and it is actually better, because for omega t on the x-axis we can have values like 0, 2 pi, or 0 pi by 2 pi, 3 pi by 2, and 2 pi, because omega t is the phase. Correct? Now we know that the resistors, the inductors, and the capacitors, they individually respond differently to the alternating voltage. Correct? For resistor, there is no phase change, so current remains Im sin omega t, phi 0. Then for capacitor, current leads, so pi becomes pi by 2 here. And for inductor, the voltage leads, so phi becomes negative pi by 2. We will see that later. But phi is the phase angle, phase difference, I would say, phase difference between current and voltage. Now the lowercase letters basically tell us that these quantities vary with time, the phase difference between current and voltage. I will also tell you, I have told you this many times, remember the word civil. Remember the word civil. If I take the first three letters CIV, C stands for capacitor or capacitive circuit. Current comes first, so current leads. Current leads voltage. If I take the last three words VIL, L signifies inductor or inductive circuit. V comes first, then I, so V leads current. And in either of the cases, the phase angle is pi by 2. So if it is capacitive circuit, then it will be plus pi by 2. If it is inductive circuit, then it will be negative pi by 2. But we generally don't specify the sign of the phase angle, but we prefer to say which one leads, which quantity leads and which quantity lags. So always remember this civil. And for resistor, phi is 0. If our circuit is purely resistive, then phi is 0. There is no phase change that is taking place. So we will now quickly revise purely resistive, purely inductive, and purely capacitive circuits, and we will also focus on the phasor diagrams and the average power spent in one cycle of the voltage, alternating voltage, and we will also revise phasor diagrams. Okay, the first and the simplest case, AC voltage applied across a resistor. This is the alternating voltage, or applying it across a single resistor whose resistance is R. We can apply the Kirchhoff's loop rule by loop rule. V minus IR is equal to 0. It's as easy as that, and V is Vm sin omega t. Therefore, I will be Im sin omega t. You can work it out. Im will be Vm upon capital R. So we say that both voltage and current are in phase. We say that the voltage and the current are in phase. What does that mean? They are in phase means they, okay, so they reach the zero value at the same time, they peak at the same time, they again come back at the same time, they go to their peak on the other side, which we call the trough because it is alternating at the same time, and again they come to zero at the same time. So during one cycle, the points or the instances of time where the voltage is where the voltage and the current peak is the same, where they both are zero is the same, where they peak on the other side is the same, and so on. This is what we call quantities in phase. Have you understood this? Yes. And also remember this, to calculate the amplitude of the current in any of the cases, and even in the general case of LCR or RLC series circuit, you always divide the amplitude of the voltage, that is Vm, by the impedance of the circuit. In this case, the impedance is equal to the resistance. In purely capacitive and inductive circuits, it is the reactance, and in the most general case, it becomes the impedance. So let me write it here. Impedance is denoted by Z, but in this case, R and Z are equal. There is also one more case where R and Z are equal, and that is the LCR circuit at resonance. Now, what about the power consumption in a purely resistive circuit? To talk about power consumption, let me remind you that instantaneous power is always given by the product of the instantaneous voltage and instantaneous current, and we prefer to talk about the power dissipated. In this case, you must talk about dissipation because resistor cannot store energy, okay, it will dissipate in the form of heat. So if we talk about average power, then which formula should I use? The average power is 1 over 2 pi 0 to 2 pi Vi d omega t. So here variable of integration is omega t, mind you. The variable of integration is this omega t, and the average power that you are going to spend over this interval is the total power spent in that interval. This is instantaneous power, so integration will give us the total power, and then because it is average, you want to talk about average power, you must divide it by the length of the interval. So in calculus notation, average value of a function on closed interval AB is given by 1 upon b minus a integral from a to b f of x dx. And that's exactly what you see here. 2 pi minus 0 is in the denominator here. B minus a, 0 and 2 pi are the limits, and the function here is the product of instantaneous voltage and current. And if you work these these things out, with V being Vm sin omega t and I being Im sin omega t, at the end you get the average power to be product of the amplitudes of the voltage and the current divided by 2. Alternately, this 2 can be split into a root 2 here and a root 2 here, and Vm by root 2 and Im by root 2 can now be called, rather they are called, the RMS voltage and RMS current respectively. In your book, that is NCERT book, the RMS values have been denoted by capital V and capital I. So they both mean the same thing, VRMS, IRMS, or capital V into capital I. Now what is the significance of RMS value? Can anybody tell me what is the significance of RMS value? Why do we define RMS values, especially in AC circuits? What is the need of that?
To compare it to DC components, म्हणजे जर का जेवढ्या RMS व्हॅल्यूचा करंट आपण एवढ्या वेळात फ्लो केला,
yes,
सेम व्होल्टेज,
yes,
तर एवढी पॉवर डिसिपेट.
yes, exactly,
मध्ये जेवढा करंट असतो तेवढा AC मध्ये RMS.
exactly. So in if we take the same circuit, rather if we take the same resistor, and instead of this alternating source, if I connect a DC source, a battery whose EMF or whose terminal potential difference is Vrms or V by root 2, Vm by root 2. And if we connect it across the same resistance R, then the current that will flow will be IRMS, which will be Im by root 2, and then the power that this will be spending, okay, average power, that will be the same as this. So see, for resistor it doesn't matter, you can talk about power per second, because both Vm and Rm, or Vrms and Rms, they are not going to change, they are constants, because this is a DC circuit now with constant voltage, correct? So in order to make comparisons and draw useful conclusions, we define RMS quantities here. So power consumption in a purely resistive circuit is Vrms into IRMS, and remember, this power consumption is not instantaneous power consumption. This power consumption is average over a cycle, correct? More thing, 1 by root 2's approximate value is 0.707. 1 by root 2's approximate value is 0.707, or around 70%. Alright. One more point, you might already be knowing this. When we talk about 220 volt AC, okay, does it mean that the amplitude is 220 volt, or does it mean that the RMS value is 220 volt? What's the correct answer? B. Yes, exactly. It's the RMS value that is 220 volts. So Vm, so this is right, this is wrong. Vm should actually be Vrms into root 2. Vrms into root 2, 220 into 1.414, that is something around 330, let me check, 311 volts around. Just remember that. But okay, the main point is 220 AC does not mean peak voltage is 220. The peak voltage is 311 volt. Okay. Now let's talk about phasors. Let's talk about phasors. So to put them, what are phasors? In short, to describe them, phasors are rotating arrows or rotating directed line segments. Rotating directed line segments. Okay, we call them phasors. Now, if they are rotating, what is their axis of rotation? In xy plane, they are fixed at origin, and they rotate about z-axis. We don't show that, but it is understood that they rotate about z-axis. So what is the purpose? First of all, we'll talk about how fast or how slow do these phasors rotate. Their angular speed, the speed of rotation of any phasor is omega. Which omega? The same omega which we talk about here. V is equal to Vm sin omega t, this omega, and I is equal to Im sin omega t plus phi, so this omega, correct? Okay. Now what is the significance of the phasors? Okay, one more point. Generally the convention is that we rotate these phasors in the anticlockwise direction. We rotate them in the anticlockwise direction, and we'll talk about two types of phasors: the voltage phasor, and because these are denoted by directed line segments, we may call them vectors. But we know that voltage and current are not vector quantities. So, well, we just utilize the I would say the terms from vectors to make our life easy in the case of complicated AC circuits. So the voltage phasor is V bar. In your book, this phasor is denoted by bold face V. So please understand that this is a rotating vector or rotating phasor, and similarly the current phasor is I bar. Current phasor is I bar, or it is bold phase current, the bold phase current. Now, how can we determine the instantaneous value of the current? To determine the instantaneous value, we project them either horizontally or vertically. In your book, they have projected these phasors on the y-axis, on the vertical axis. For instantaneous values, we project them on y-axis or on x-axis, but here in your book they have projected them on y-axis. So what is the benefit of that? If you project them on y-axis, then this quantity here will be magnitude of this into sine of omega t1, isn't it? Sine of omega t1, because this is the cosine component, so this will be sine. So that gives us the instantaneous values, and we already know what the instantaneous values are. V is equal to Vm sine omega t and I is equal to Im sine omega t. And now let's talk about the main part. What's the use of the phasors? Use. Helpful in determining the phase angle or the phase difference. Useful in determining the phase difference between voltage V and the current I, because we know that in RLC series circuit, phi can range anywhere from negative pi by 2 to positive pi by 2, with special cases being phi equal to 0 if it is purely resistive, and phi equal to plus pi by 2 or minus pi by 2 if it is purely capacitive or purely inductive. Okay, now this is the phasor diagram for a purely resistive circuit where the voltage and the currents are in phase. So the gray phasor of current forever coincides with the blue phasor of the of voltage, okay, voltage phasor, and they kind of rotate together. And therefore the phase difference between them is 0. So they peak at the same time, they go to 0 at the same time, they peak in the other direction at the same time, and so on. So this is the phasor diagram for a purely resistive circuit. Projections give us the instantaneous values. If you remember, in our regular lectures we also saw the animations of these. Alright, so these are phasor diagrams. Sachat, क्या doubt है? Any doubt in phasors? Okay. Now let us talk about what happens when we connect an inductor across the alternating voltage. It can be worked out. We will obviously not be doing that in this class, but it can be worked out that using Lenz's law and Kirchhoff's loop rule. By loop rule and Lenz's law, we get this equation: V is equal to V minus negative L di by dt is equal to 0. Okay, I hope you understood that. This V comes from the source, and this negative L di by dt, this comes from the back EMF due to the solenoid or due to the inductor. Correct? Now what we do is we assume that the current is Im sine omega t plus phi. We assume that, and we now substitute this particular value of or rather this function here, and then we solve the differential equation, which is a simple integral. We also mention that the constant of integration is 0 for obvious reasons, and then if you do that, you can get the value of amplitude of the current in terms of three quantities. Quantity number 1 is Vm, the amplitude of the voltage. Quantity number 2 is the inductance L, and the quantity number 3 is the frequency, the angular frequency omega. And the product of the angular frequency omega and the inductance, we call it XL, and the name is inductive reactance. The name is inductive reactance. Obviously its SI unit will be ohm. Its SI unit will be ohm, and using omega L we get an equivalent unit of ohm, and that will be Henry radian per second or Henry per second, right? Because, well, we don't mention radian, and omega is radian per second, so per second, and L is Henry, so Henry per second is ohm. That is inductive reactance. And what about phi? What about phi? Remember civil. This is an inductive circuit, so the voltage is going to lead the current by pi by 2. So this value phi will be negative pi by 2. This value phi will be negative pi by 2, or you can just say phase difference is pi by 2 with voltage leading the current. And now what does that mean when we show it on the phasor diagram? In phasor diagram, it means that the voltage phasor in the blue color here and the current phasor in the gray color here, they will always make an angle of 90 degrees. You can see that. You can see that. Okay, this is the 90-degree angle. And more importantly, because our phasors are rotating anti-clockwise, when I say that voltage leads current by pi by 2, the current phasor will kind of follow the voltage phasor, but the angle between them will always be equal to 90 degrees. Correct? And you can see that I is equal to Im sine of omega t1 minus pi by 2. That negative pi by 2 basically tells us that current is lagging voltage, or voltage is leading the current. Now, if you plot the graphs of instantaneous values against omega t, voltage leads means voltage will peak first and then the current will peak. Okay, in any given cycle. In any given cycle which starts at voltage's instantaneous value being 0. Voltage leads first, voltage peaks first and then the current will peak. Please try to understand that. When current lags, it will peak later in any given cycle with voltage starting at 0. Have you understood this? Okay, what I said is, suppose the blue graph is given to you. Blue graph is that of instantaneous voltage, and we are assuming that V is equal to Vm sine omega t, and any sine curve will always pass through origin. Is that clear? Huh. Now, under steady states, that means we have turned on the switch and then you have allowed some time to pass. What you will find is, at any given instant, let's say the voltage has peaked earlier. Okay, so you take a cycle after the current has established, you take a cycle where voltage is at 0 and the voltage will grow. It will go to its peak. What will happen to the current flowing inside? You can't show the direction here, but let's say this is the current flowing through the inductor and or through the circuit. The sense of this voltage, okay, let's say it's the positive in this way. Current is going to peak after some time in the same cycle. Okay, when will it peak? It will peak when this gap is pi by 2. This gap is pi by 2, and it will peak later because voltage leads current. Now, what does it mean, leads the current? It will peak first and the current will follow that, and this is pi by 2 because this is the omega t axis. I hope you understand what I explained now. Okay, other people तुम्हाला समझता है? Okay, okay. What about average power consumed in a circuit? The average power, it can be worked out, and we can prove that the average power is 0, assuming that it is a pure inductor. Assuming that it is a pure inductor. Okay, it doesn't consume any power, it stores and then it releases the energy again in the circuit. Now, this is a graph which will help us understand how the instantaneous power fluctuates in one cycle of alternating voltage and therefore current across a pure inductor. To begin with, I would like you to focus on the blue curve first. This blue curve is actually cosine curve, but it hardly matters now because, I mean, if you know the phase difference between the two, voltage and current, that is not going to be any tip of any difference. But the point here to be noted is voltage has peaked, and after that the current has peaked here. Okay, this is the current, this curve. So the current has peaked here. Don't worry about the amplitudes now, because the amplitude of current is amplitude of voltage divided by the inductive reactance. So have you followed the two curves? The blue curve is the voltage curve, and the black curve, not the dotted one, but this curve, the one below that is the instantaneous current curve. Have you understood this? Okay. Now you note that instantaneous power is instantaneous voltage into instantaneous current. This is small p, okay? This is instantaneous power. Instantaneous power. It is V into I. And what is V? Vm sin omega t. What is I? I is Im sin of omega t minus pi by 2. Okay? Minus pi by 2. Okay. Now let us talk about flux. It should not be a surprising thing that flux is in phase with current, because in our yesterday's lecture we have seen that flux linkage phi b is directly proportional to current. This is self-inductance now, not the mutual inductance. So because flux is directly proportional to current, flux and current will be in phase. So that's why you see the same two curves. Alright, now let us come to the power curve. Let us come to the power curve. Okay. Now you can see that the frequency of the power, fluctuating power, is double the frequency of voltage and current. What I mean by that is, during the interval where current completes one cycle, the instantaneous power completes two cycles. The instantaneous power completes two cycles, one corresponding to current flowing in this direction, okay, and or rather the magnetic field in the inductor in that direction, and the other cycle corresponds to magnetic field in this direction. Okay, that is why you see one cycle and then the other cycle. Now let us talk about this table. Suppose I'd go to the first phase. Okay, I shouldn't say phase here. Let's say, well, cycle. Let's say we talk about the first quarter of the cycle. In this case, you see that the voltage is positive but decreasing, the current is positive plus but increasing. Okay, so what will happen to the power? The instantaneous power at the beginning of this cycle will be 0 because current is 0. It will peak here and again it will go to 0 at the end of this quarter of the cycle. And what is the reason here that it is 0? It is 0 not because current is 0, but it is 0 because voltage is 0. So we have now covered this part of the cycle, the power cycle. Have you understood this? Okay. Okay, now let us so this basically refers to magnetization. This refers to the establishment of the magnetic field inside the inductor. Okay, now what will happen? The voltage has now reversed its polarities. Okay, so the voltage has become negative, so to speak. So this leads to you can say demagnetization of the inductor. So the magnetic field inside the inductor is now going back to 0. Okay, it will go here. Now look at the second cycle. In this case, the current's direction is opposite to that of voltage. Voltage is negative, current is positive, but current is decreasing. Okay, current is decreasing but positive, and voltage is decreasing, but it is increasing in magnitude, although the sign is negative. Okay, so what will happen to the power? It will be 0. It will okay, it will now peak, so to speak. It will peak here, okay, trough, and then it will again come back to 0. Why will the instantaneous power be 0 at the end of the first half of the cycle? It will be 0 because the instantaneous current there is 0. Okay, so we have now completed 0 to 1 and then 1 to 2. We have completed 0 to 1 and 1 to 2. Okay, have you understood this? Yes? So what does this indicate? The first part, this hatched portion here indicates that the magnetic field establishment has begun. Okay, and the second part basically tells us that the magnetic field inside is again going back to zero. Well, just look at flux. Okay, just look at flux. Now what has happened, the current has reversed its direction. Now let us look at the third part of this quarter cycle, 2 to 3. Okay, now why will the instantaneous power be positive here? The instantaneous power will be positive here because both the current and the voltage are negative. Voltage is negative but increasing, that means its magnitude is decreasing. And what about current? Current is negative but decreasing. Current is negative decreasing, it means its amplitude, its magnitude is increasing, but the sign is negative. So because both are negative, the power will be positive. This indicates the establishment of magnetic field inside the inductor in the opposite direction. So it will be 0 at the end of this, it will peak and it will again go to 0. Alright, and if you repeat the same analysis, so we have now completed this cycle. Now the decay of that magnetic field will begin in the last quarter of the cycle, 3 to 4. Voltage is now positive and increasing, but the current is now negative, but it is also increasing, it is going to 0. So the power cycle will look like this, and it will start at 0, peak, and it will again, or trough, and it will again go to 0. Have you understood this? They might ask you this in the paper, or as a multiple choice question this can come. Okay, and why are there two cycles of power fluctuations when there is only one cycle for voltage and current? The answer to that is the establishment of the magnetic field in both the directions. In LC oscillations, actually that becomes clear, but unfortunately for this year they have omitted LC oscillations. But anyways, have you understood this? Have you understood this graph? If you understand this, then you can very easily understand the same or similar graph of purely capacitive circuit. Hey, समझला? Okay. Okay. Now let us go to AC voltage applied across a capacitor. AC voltage applied across a capacitor. In this case, we are going to again use loop rule, and also an important relationship which we studied in the second chapter. Right? What was that? C is equal to Q by V, or Q is directly proportional to V. The net charge on any one plate of the capacitor is directly proportional to the potential difference between the plates. Okay, and the constant of proportionality being C. So V will now become Q by C, and that Q by C with the negative sign will come here. Okay, Im is always Vm upon the impedance. In this case, there is no resistance, there is no inductance. So we define a quantity. What quantity is that? Xc is called as capacitive reactance. Capacitive reactance. And what is the formula for capacitive reactance? It is 1 upon omega c. The SI unit of this is still Henry, and you can also figure out the alternate unit of capacitive reactance by taking the SI unit of 1 upon omega c. What about the phasor diagram? What about the phasor diagram here? Remember civil. So now we need to consider the first three letters, right? First three letters. Current I comes first, V comes later. So current will lead the voltage. So phi will be pi by 2, positive pi by 2 rather. So instantaneous current will be I is equal to Im sine of omega t plus pi by 2. You can work it out, but we already worked it out in our regular lectures, and Im is Vm upon Xc. Just like the average power was 0 over a cycle for purely inductive circuit, it is 0 for purely capacitive circuit as well. So for phasor diagram, let us consider a particular instance of voltage. Okay, let us consider a particular instance of voltage. Because the phase difference is now positive, current leads. the current phasor will now lead here. That means to draw the current phasor at this instant, you will rotate the voltage phasor in anticlockwise direction by 90 degrees, and that will be your current phasor. And as I said, leading means it peaks first. Okay, so if voltage starts at 0, you can see that the current has already peaked, and the phase difference here is pi by 2. This is pi by 2. This is pi by 2. Because on the x-axis we have not t, but we have omega t itself. Have you understood till this? Alright. Now let us analyze a similar figure for purely capacitive circuit, and in this case, well, they have not stuck to their notation or the color for voltage, but anyways, so again there are 4 quantities here. Which 4 quantities? Instantaneous voltage Vc across the plates of the capacitor, the net charge on any one plate of the capacitor, the instantaneous current I, and the instantaneous power P. And in one cycle of alternating voltage or current, the capacitor charges and discharges twice, and that is why you can see the 2 power cycles here. You can see the 2 power cycles, one to the left of this and one to the right of this. Again, as usual, the hashed one represents the power cycle. And let us also talk about the other 3 curves here. Okay, let us talk about the other 3 curves here. The sine curve here is the voltage curve. The sine curve here is the voltage curve, which begins at 0, and then this is the sine curve of the voltage. Because the current leads, just a second. Yeah, okay, correct. Because the current leads, current has peaked first, and then this is the current curve. This is the current curve. The voltage and the charge, they are in phase, isn't it? The voltage and the charge, they are in phase. Q is directly proportional to V. In the first figure, for inductive, it was flux and current. They are in phase. In this case, charge and voltage, they are in phase, right? Okay, and this is the power curve. So have you understood all the 4 curves? The dotted one is the charge, and the one above that, which is in phase with Q, the charge one, is the voltage across capacitor, and this curve, the cosine curve here, is actually the current curve, and the one with the hatching is the power curve. Is that clear? All the 4 curves now?
Oh.
Okay, now let us talk about the different cycles. Let's talk about the 4 cycles, or the 4 quarter cycles, which constitute one cycle of voltage and current. 0 to 1. What is happening? The capacitor will charge. That means electrons from one plate will be transferred to the other plate through the external wires and through the source. That indicates the charging of the capacitor. In this case, the instantaneous power will be positive. Isn't it? The instantaneous power will be positive. Why will the instantaneous power be positive? Because the voltage is positive and so is the current. If you look at this figure, this part of the figure, both voltage and current, they are positive, so instantaneous power will be positive. What is happening to the voltage? Voltage is going from 0 to max, okay, and the current is going from max to 0, but both are positive. So power will start at 0, it will peak, and then it will again go to 0. That's the first part. Now second quarter. What is happening to the current? The current is negative and decreasing. But the voltage is positive. And it is decreasing. Okay, so again here at the end of the second quarter of the cycle, the power will again be 0, instantaneous power will be 0, and this indicates the complete discharging of the capacitor. Okay, so this is one power cycle. It has charged and it has discharged. Okay, 0, rough 0. Now let us go to the third quarter of the cycle, 2 to 3. Both current and voltage in this case are negative. Okay, the voltage the voltage is decreasing now, it's negative. And what is happening to current? Current is actually increasing, but it is still negative. Still negative. So this indicates the charging in the other direction. What I mean by that is, let's say here the capacitor charged like this, suppose. Positive, positive, negative, negative. In this case, how will it charge? Negative, negative, positive, positive. This is how the capacitor will charge. Okay, so that is from 2 to 3, and then it must discharge as well. So in the last quarter of the cycle, that is from 3 to 4, the current is positive, the voltage is negative, discharging will begin, the power will, in this case instantaneous power will be negative. Okay, so this completes two power cycles. Two power cycles basically mean the capacitor charges and discharges twice in every cycle of current or every cycle of voltage. Have you understood this? Okay, fine. Now let's move on. Let us now go to AC voltage applied across LCR series circuit, which means an inductor, a capacitor, and a resistor are connected in series. This is where phasor diagrams come to our rescue, because the actual analytical method involves solving a second order differential equation, and you don't have that in your syllabus right now. You will study that in your next year engineering maths. But anyways, you have a method which assumes a solution. The solution. That is one way to do that. But okay, anyways, so what does the phasor method tell us? Phasor method tells us that assume that the current has this phase difference of phi with the voltage. The current has a phase difference of phi with this voltage. And now, please pay attention. Now what we are going to do is, because R, C and L are in series, the voltages across R, C and L, they will be different. Okay? Uh, and therefore we split them. Okay, we basically split the input phasor. We basically split the input phasor V bar into three: V across resistor, V across capacitor, and V across what? And V across inductor. V across inductor. Now while showing these things on the phasor diagram, what I'm going to do is, I'm going to remind myself that current, which will be the same for all three, because well, they are in series, the current will be same. The current will be in phase with what? The current will be in phase with VR. Correct? The current phasor will be in phase with VR bar, and you can see the coincidence of the current phasor and the voltage across resistor R. Okay. Now, what will I do, or what should I do rather, for VC and VL, these two phasors? I know that in purely capacitive circuit, current leads voltage. Okay, current leads voltage. So I must show the VC phasor to the right of the VR phasor or the current phasor, and similarly the inductor phasor should be shown ahead, because there the current leads the voltage. Have you understood this? Have you understood this figure or no? Okay, now please note, here we have not yet shown the main voltage phasor. We have not shown the main voltage phasor in figure A. Instead, we have shown four phasors: the phasor voltage across R, the phasor voltage across C, the phasor voltage across L, and the instantaneous current, because instantaneous current is the same. Because this is not parallel combination, this is a series combination. Is that clear? Right? At any given instant t, the current, okay, let's say omega t plus phi is the phase of the current, where omega t is the phase of voltage, instantaneous voltage. That's the main voltage. Okay, but in this case VC lags VR by pi by 2 or I by pi by 2, and VL leads VR or I by pi by 2. Have you understood this? Okay, now let us analyze the figure B. In figure B, what we are going to do is, we are going to add VC and VL vectorially. vector addition. Now this figure assumes that V bar C is in magnitude greater than V bar L, and that is why it is towards this side, VC plus VL. You can see the length of VC being decreased, and VR is already here. VR, this phasor, the green one, is already here. So we can now add VR bar and VC bar plus VL bar vectorially, and what will that give me? That will give me the net voltage, net applied voltage. This one, correct? VR bar plus VC bar plus VL bar. This is the net voltage. But what is the angle between, or what is the phase angle between, phase difference between the instantaneous voltage and the current which is along VR bar? That is phi. So this is phi and this is omega t. Please try to understand how these figures are being constructed. हे कळालंय का तुम्हाला? नक्की? Okay. Now if you understand this, then we can very easily construct a triangle which we call the impedance triangle, but I'll come to that in a while. Let us now talk about the actual equation which actually produces the solution. So here again we are applying loop rule. We are applying the Kirchhoff's loop rule. So Vm sin omega t is the applied voltage drop across resistor. Vr is IR. Voltage across capacitor C is Q by C, we know that, so this is Vc. And the voltage across inductor, we know that, back EMF, it is L di by dt. So here we have applied everything, Ohm's law, Lenz's law, and the capacitor expression. So this is VL equal to 0. This is by loop rule. Now here by differentiating, or rather by assuming another angle theta for Q is equal to Qm sin omega t plus theta, you can arrive at the expression for theta and phi and so on. I'll not do that here, but I'll just state the important results. There are two things now to be noted in any AC circuit. What is the amplitude of the current? Okay, because the frequency never changes. What is the amplitude of the current? And second thing is, what is the phase difference between the instantaneous voltage and the instantaneous current? In this case, this is the most general case, let me tell you. Amplitude of the current is given by Vm divided by what we call the impedance of the circuit. Impedance of the circuit, and its formula is root of R square plus bracket Xc minus XL the whole square, or XL minus XC the whole square, doesn't matter. And what is tan phi? You can draw the impedance triangle, and impedance triangle is actually this triangle. Impedance triangle, let me shade it now in red color. It is okay. Let me hatch it in red color. It is actually this triangle. Okay, it is actually this triangle with the resistors and reactances instead of voltages. Okay, but you can easily figure out how these things have come here. Alright, so this is the same phase angle phi, which is this. So these triangles are basically similar. Okay, these triangles are similar. Okay, now can you tell me what is tan phi? Yes, tan phi is Xc minus XL divided by R. Okay, or you can also talk about cos phi, which will later on be called as power factor. It is R upon Z. Okay, I have omitted the mathematical treatment, but I have told you how to deter how this triangle, how this impedance triangle has come up. How this impedance triangle has come up. It has come up because of this original phasor triangle. Is that clear? नक्की कळालं ना हे? परीक्षेत येऊ शकेल. Explain this. असं. कळलं? ठीक आहे. Okay. Now there are multiple cases, or infinitely many cases possible, one each for every real value of phi. But in your textbook, they have plotted this phasor diagram where they say that Xc is greater than XL. When this happens, we call it predominantly capacitive or capacitive. Predominantly capacitive. When is this going to happen? This is going to happen when capacitive reactance Xc is greater than inductive reactance XL. In other words, 1 upon omega C, when it exceeds omega L, it becomes predominantly capacitive. So what does that mean? That means current will lead. Current leads voltage by the angle phi given by tan inverse of Xc minus XL divided by R. Xc minus XL divided by R. Had it been the other case, it would have been tan inverse of XL minus Xc by R, and we would have said current lags voltage by that angle. Okay? So let's look at the phasor here. This is the voltage phasor shown at some instant t1. Omega t1 is the phase. Omega t1 plus phi, phi is positive, that will be the phase of the current. Now because current leads here, the current is going to peak first. Look at the gray curve here. It has peaked here. It has peaked here. And the phase the phase change after which the voltage will peak, this phase change is equal to phi. They have shown that already in the figure. This is phi. Have you understood this? Okay, so I'll give you this as a homework question. Show the variation for XL greater than XC. Okay, show the variation for XL greater than XC without changing blue curve of V. Okay, you keep the voltage phasor as it is, show one cycle, and well, you know actually what to do there, isn't it? The current will now be somewhere here because it is going to lag, and you can do whatever you want there. So can you do that on your own? That is the homework question. ठीक है, येईल करता है. हो तू पण तुम्ही करा ट्राय. तुम्ही जर नाही केलं तर तुम्हाला वाटेल तुम्हाला समजलंय, पण मग परीक्षेत प्रॉब्लेम येऊ शकेल. ओके, सो जरी व्हेरिएशन म्हणजे जर तुझं सर्किट प्रिडॉमिनंटली इंडक्टिव्ह असेल, ओके, तर तुझा फाय जो असेल तो काय असणार आहे, जे काय असेल ते, जर करंट लीड करेल व्होल्टेजला का लॅग करेल ते तुला आधी ठरवलं पाहिजे, इफ इट इज प्रिडॉमिनंटली इंडक्टिव्ह. आता फायची स्पेसिफिक व्हॅल्यू आपल्याला दिलेली नाही आहे, नसणार आहे, कारण आता ऑब्व्हियसली दिस इज ओनली अ सिमॅटिक, राईट. मग फायची एखादी अप्रोप्रिएट व्हॅल्यू घेऊन, किंवा नाही घेतली तरी चालेल. तुला काय माहिती आहे, जर प्रिडॉमिनंटली इंडक्टिव्ह असेल तर व्होल्टेज लीड करेल. सो जर मी व्होल्टेजचा फेजर असा दाखवला इथे, तर मला करंटचा फेजर कसा दाखवला पाहिजे, त्याला लॅग करणारा दाखवला पाहिजे ना. दिस इज हाऊ इट विल बी. सो इफ दिस इज ओमेगा टी, this will be phi. Is that clear now? Now, well, I've already partially answered the question for you. Now let us consider this. आता तुम्हाला एक काळजी घ्यायची ते प्रोजेक्ट करताना. This instance that I have shown here, it has to be somewhere in the second quadrant, isn't it? Because pi by 2 is it, and it is already crossed pi by 2, so its amplitude is actually, its magnitude is actually decreasing. So this is that case. Oops, sorry. Anyways, you understood it, right? थोड़ा समय ते peak वरती झाला. This is that instantaneous value. So how will the current look here? That is what I want you to draw. ठीक है? For the same cycle. All right. Now let us talk about resonance in LCR series circuit. What does resonance correspond to? Resonance corresponds to the maximization of amplitude of current without changing, or for a given set of current for a given set of values of R, L and C. What is the condition? How can we maximize this? And see, I'm not saying maximizing current, I'm saying maximizing amplitude of current, because I already know that current is alternating. So this condition of maximization can be achieved by minimizing the denominator. Okay, and what is the condition? So to maximize it, we must minimize impedance. We must minimize the impedance. Okay, now minimizing impedance means, well, we are not allowed to change this, so XL must be equal to XC. XL must be equal to XC, so omega L must be equal to 1 upon omega C. So that gives me omega as 1 upon root LC. Okay, 1 upon root LC. This is the resonating frequency, correct? And that will maximize the amplitude of the current flowing through RLC series circuit. Is that clear? Okay. So the circuit will behave as if it were purely resistive, but well, it's not, because it will also have consists of an inductor and a capacitor. Okay. Now let us analyze this figure from your book, which talks about variation of amplitude of current. I'm not saying variation of current itself. Current always varies, right? Because current changes sinusoidally, we know that. So this is amplitude of current. So what is amplitude? Amplitude basically refers to how large is this value. That is current amplitude. That is the current amplitude. Okay, that is the current amplitude. And of course, if we are not changing R, we are not changing L, we are not changing C, we are not changing Vm, then the amplitude of the current must change, or rather it does change with frequency omega of the applied voltage. So if you change omega, you can get resonating condition, or you can get resonance. Alternately, you have three parameters here, omega, L and C. Alright, so if you know two of them, then you can adjust the third one. It is actually C that we change in tuning the radio circuits and so on. When we tune the knob, it is actually the capacitor C that changes, and then it can catch the frequency of that particular radio station, and then the current amplitude increases, and then you can hear the signal, whatever is being said on the radio. Alright, okay. So this is a textbook figure. They have mentioned that the inductance is 1 millihenry, capacitance is 1 nanofarad, and the peak voltage is 100 volt. The amplitude of the voltage is 100 volt, and the omega, the frequency, is in mega radians per second. Okay, this is mega radians per second. The resonating condition, you can very easily calculate the frequency, 1 upon root LC. I'm not going to do that. It's very simple, right? You take the product of this, and then you take the square root, and then take the reciprocal. It will turn out to be omega resonating equal to 10 raised to 6 radians per second. 10 raised to 6 radians per second. And other parameter that they have changed here is the resistance of the circuit. The first one, the blue curve corresponds to a smaller value of resistance. So Im will be greater, because, well, you know that Im is Vm upon R. If R is smaller, then Im will be greater for the same set of other values. And this is the gray curve. This is the gray curve. So what do you see here? If the resistance is smaller, the resonance is sharper. If the resistance is smaller, the resonance is sharper. And if the resistance is larger, then the resonance will be flatter. So you have a factor called quality factor to measure the sharpness of the resonance, but that has been omitted, so I will not talk about that. But have you understood the curve? Note that it is symmetric. Note that it is symmetric. Is that clear? Okay. Okay. Fine. Let's now talk about another important dimensionless parameter called the power factor. We have seen that if our circuit is purely resistive, then phi is 0. If our circuit is either purely inductive or purely capacitive, then the phase angle is pi by 2, and if we have an RLC series circuit, then the phase angle can be anywhere from negative pi by 2 to positive pi by 2, with the condition of resonance giving us equal to 0. Okay, if you work out the expression for the average power over one complete cycle of voltage, that means omega t changing from 0 to 2 pi, or you can take any interval of length 2 pi, and if you calculate the average power, then you will get Vrms into Irms into cos pi. Okay, remember Vrms is Vm by root 2, Irms is Im by root 2, and then this additional term cos phi pops up. That's integration, and you can also write it as I squared Rms into Z cos phi, where this Z is the impedance of the circuit. This Z is impedance of the circuit. What is the formula for impedance? Let me again write it here. It's root of R squared plus XC, or well, XL minus XC or XC minus XL the whole squared. What are XC and XL? Capacitive reactance and inductive reactance. XC is 1 upon 2 pi FC or 1 upon omega C, and XL is 2 pi FL or omega L. Okay, so the average power consumed in one cycle, it not only depends on the RMS values of voltage and current, or the RMS value of the current and the impedance, but it also depends on phi. It also depends on the phase angle between the voltage and the current. Now, this result is kind of counterintuitive. Why is that? Because we know that resistance is the only power consuming device, okay, whose net power consumption is non-zero or positive over a cycle, whereas for capacitor and for inductor, the net power consumption is zero, right? For ideal capacitor and ideal inductor. So we might expect that the power factor or this term cos phi should not have any role to play. It will just be the average power will just be Vrms into Irms, but that's not the case. Although inductor and capacitor do not consume power over the cycle, you know that both of them act as energy reservoirs. Inductor can store energy in the form of magnetic potential energy in the magnetic field in between the space, okay, in between the inner space, right, between the coils, between the coil, and capacitor can store energy in the form of electric potential energy in between the space that exists between the plates of the capacitor. So though that whole thing affects the average power consumption, and that is reflected in the appearance of this cos phi. The mathematical derivation is already known to you. Okay, now let's talk about 3 or 4 special cases in which this power factor determines the average power consumed. Number 1, if we have a purely resistive circuit, then what is the impedance Z? The impedance Z is equal to R, and the power factor is equal to 1 because phi is 0. Correct? If we have a purely inductive or capacitive circuit, then what is phi? Phi is pi by 2. Okay, we can't write it as plus or minus pi by 2, it doesn't matter. But what matters is cos phi is 0. Cos phi is 0. And we already know these two results as well, that the average power consumed during or for a purely inductive or a capacitive circuit is 0. So P average is 0. Okay, now suppose you have RLC series circuit at resonance. Now at resonance, what happens again is this. XC becomes equal to XL, therefore impedance Z becomes equal to the resistance R. Please note, the first case and the third case are different. In the first case, C and L, they both are 0 in purely resistive circuit, whereas in RLC circuit as resonance, C is not 0, L is not 0, but because the condition XC being equal to XL is there, it prevails. The XC minus XL term cancels out, so the impedance again becomes equal to resistance, okay, numerically, and we get maximum power dissipation. Maximum power dissipation. Because, well, cos phi is 1 here. Have you understood this? Yes? Okay. Okay. The LC oscillations, they have been omitted, right? So I will not talk about them. But again, yes. But again, you can clearly see that. Okay, let me just in one or two statements summarize this. LC oscillations refer to a fully charged capacitor connected across an inductor. That's it. What happens is the capacitor discharges, its energy will be stored in the form of magnetic field, magnetic potential energy in between the inductor. Then the inductor will lose its magnetic field, the capacitor will charge in the other direction, and this will continue forever, theoretically. What actually happens is the inductor wire as well as the connecting wires, they have non-zero resistance, so some energy will be dissipated there. And this other thing is that whenever any charge accelerates, it will emit electromagnetic radiation according to Maxwell's theory. Both these things actually lead to uh, dying out of oscillations. Okay, but in theory, yes, LC oscillations will continue forever. And you can also draw parallels between the mechanical systems of spring mass oscillation and electrical system of LC oscillations. Remember, inductance plays the role of mass. These are analogies, and we have also already seen this in magnetic potential energy being half Li squared and kinetic energy being half mv squared. Correct? So here velocity is v, here current is I, displacement x, charge q, force constant, that is kx. Okay, force per unit displacement, that is force constant, and here it is the reciprocal of the capacitance, and everything else is more or less the same. Half kx squared is the spring or elastic potential energy, half mv squared is the kinetic energy, net energy remains constant. Here the dissipative agent, okay, here the dissipative agent is friction, or the agent that takes out energy from the system, and here the dissipative agents are EM radiation and the resistance. Okay, EM radiation and the resistance. Okay, we have discussed this in detail in our regular lectures, so I will not go through these things again, but please note that spring is analogous to capacitor and the moving block is analogous to inductor. Everything else can be very easily worked out. And now let's go to the last part, that is transformers. The purpose of transformers is either to increase or decrease the amplitude of the voltage. And what is the working principle of transformers? The working principle of transformers is mutual induction. Working principle of transformers is mutual induction. We know what that means because we have revised the previous chapter, electromagnetic induction. So a transformer consists of two coils, the primary and the secondary. Generally, the primary coil is connected to the source and secondary coil is connected to the load. You can have two orientations, either they are wound on the same iron core or they are wound on different iron cores of the same piece. Okay, so there will be flux linkage and therefore induction of current or voltage. We can develop these relations assuming the transformer to be an ideal transformer, which basically means that no flux leakage takes place. Then the wires are not resistive. Okay, wires are not resistive, so there are no power losses. So when all the power that is associated with the primary coil is completely transferred to the secondary coil. Generally, the efficiency is somewhere around 80 to 85%, but it can be improved. There are also other reasons for the loss, like hysteresis loss is there, and other losses, flux linkage and so on, flux leakage and so on. Okay, but the most important, or rather the only mathematical relation that you have here is this. Ns and Np denote the number of turns in the secondary coil and the primary coil. It can be shown that Ns upon Np is the same as Vs upon Vp, where Vs is the voltage of the secondary coil and Vp is the voltage of the primary coil. and this ratio, it is IP upon IS. Remember, it is VS upon VP here, and it is IP upon IS. P stands for primary, S stands for secondary. When NS, okay, so let me write VS here. It is VP into NS upon NP. When NS is greater than NP, that means when you have more number of turns in the secondary coil than in the primary coil, then Vs will be greater than Vp. This corresponds to a step up transformer. Okay, step up transformer, and the other case is Ns less than Np, which implies that Vs will be less than Vp, and this is called as a step down transformer. Okay, the advantages of high voltages during transmission, they are or their benefits, it's clear that minimizes the heat loss due to the resistance of the conducting wires or transmitting wires. Okay, fine. So that completes AC circuits as well, or alternating current. And now there's only one chapter remaining that we need to revise from electricity magnetism, that is electromagnetic waves, which we will do in the next class.